Okay, today I'm going to cover basically two kind of mini topics. Yes. I just did, yep.
I was looking at that.
It happens. Happens the best of us. Okay, we are done talking about new coordinate systems. We talked about Cartesian coordinate system. We talked about normal and tangential coordinate system. We talked about radial and transverse coordinate system, and that's all of the coordinate systems we're going to talk about in this class. Now we're going to kind of dust off the rest of particle kinematics. That's all we've talked about right now is particles and their kinematics. There's two kind of special topics that we're going to talk about. So sometimes we can have what we call dependent motion, where the motion of one particle almost entirely defines the motion of another particle, usually because they are attached to each other in some way. So that's what we're going to talk about for dependent motion. And then separately, we're going to talk about relative motion. So relative motion is where you again have two different particles moving through space. And the motion of one particle, it doesn't completely define the motion of the other particle, but it tells us a little bit about what that other particle is doing, okay? So we might define the motion of the second particle relative to the first particle, all right? So both of the topics today, we're talking about two different particles moving around in the same space. So for dependent motion, I'm drawing kind of like the simplest example of some of the systems that we're going to look at. And for the most part, these systems involve a frictionless pulley and an inextensible rope or cable or cord or whatever you want to call it. That's kind of what defines these types of systems that are dependent. So and in fact, we're probably, at least in this section, we're not going to worry about the mass of the pulley. We're going to pretend that the pulley itself is massless and frictionless, so it doesn't resist motion at all, and that cord cannot change length. So inextensible means that it cannot stretch, it can't get longer, and it can't compress. It can't get shorter. All right? So when two particles are connected by this inextensible cord, it means that the motion of one of those particles entirely defines the motion of the other one, but they're not exactly the same. What do I mean by that in the context of this picture here? If I know something about the way that particle A is moving, what do I know about particle B? Yep.
It's doing the opposite of that.
Okay, it's moving with the same amplitude, but in the opposite direction. So the pulley changes the direction of the motion. So if A goes down, B goes up, but they are moving at the same velocity and the same acceleration. Okay? We're going to talk about how to analyze even more complicated systems. So here's another one, another example of a dependent motion problem. Sometimes we'll talk about, well, not sometimes, a lot of times in this class, for whatever reason, we talk about blocks on slopes a lot. So let's say we have two different blocks, maybe a block A and a block B, and they're connected by a rope that goes over a pulley. I'm going to try to make this colorful. Like so. And in this case, Samuel, tell me again, if I know about block A, is the motion of block B necessarily exactly opposite? No. However, if block A moves up and to the right, block B moves down and to the right. Okay, so they're still very related. And in fact, we can write a differential equation that relates the two movements, and we'll learn how to do that. So for this for this system here, the way that I have it drawn, I'm going to choose a couple of special locations that I want to keep an eye on. And this is one of those choices that comes through practice, and it's kind of hard to describe exactly how I'm choosing it, but I'll do my very best. So I'm going to say that a particular section of this system that I want to keep a close eye on is the section between block A and the edge of the pulley, and I'm going to call that distance SA. I'm also going to keep a close eye on the distance between block B and the edge of the pulley, and we'll call that SB. Does anyone know, maybe you did some reading ahead, so bonus points, not really, but in my mind, bonus points for answering this question. Do you know why I'm kind of ignoring this little piece of rope in the middle? Yeah, any idea? Aha! It is a constant distance. That distance from where the rope very first attaches to the pulley and very first detaches from the pulley, that distance will never change. If this block is way over here, there will still be that much rope in contact with the pulley. If it's way over here, that much rope will still be in contact with the pulley. This is in comparison to SA and SB, which will change in distance over time as the blocks translate over this weird ramp thing. Okay? So here's how I write this relationship for how these two kinematics of these particles are related. The very first thing I want to do is I want to write down an equation for the length of the rope. Oops. So let's say I'm going to say I have this total distance of the rope. The rope has some total length. Can I write the length of the rope in terms of the things that I have notated on my image? What would it be? What would that expression be?
SA plus SB.
Okay, great. SA plus SB. Is that it? Yeah, plus the constant. Yeah, absolutely. So I could call this maybe a distance C that never changes. So we'll go ahead and throw it in there just to be complete. The length of the rope is whatever SA is plus the constant amount plus SB. Now I said this rope is inextensible. Remind me what that means again?
Can't stretch one.
Okay, tell me in terms of this L rope.
It's a constant.
L rope is a constant, which means that if I take a time derivative of L rope, what is that equal to? 0. Okay, so L rope dot is equal to 0. An extensible rope. Okay, so we get 0 is equal to the time rate of change of SA plus the time rate of change of SB plus the time rate of change of C. Is there anything else that goes to 0? The time derivative of C, right? By definition, this is a constant amount. So it never changes in time. All right. Now tell me, how might we relate this change in distance SA to the way that particle A is moving?
You say that again?
Yeah, so I've defined this time rate of change of SA. SA is the distance between particle A and the edge of the pulley. And we know how, we maybe have an expression, SA dot, of how that's changing in time. Is that related in any way to maybe like the velocity of block A?
Yeah.
How?
Because that's the block move, so this would go
It's the exact same rate. Perfect. So my velocity of A is going to be the amount SA dot in the direction, depending on whether SA dot is increasing or decreasing, we know we can define the direction of this velocity. Okay, so let's say SA is decreasing in time. We have a negative time derivative. Does that mean that SA is moving up and to the right, or sorry, does that mean block A is moving up and to the right or down and to the left? SA is getting smaller and smaller and smaller. Yeah. The distance between the block and the pulley is getting smaller and smaller and smaller, which means that SA must be moving closer to the pulley. So the velocity of block A will be SA dot in the upwards to the right direction. And I don't have a vector or a unit vector to describe that for this image because we haven't set any angles or anything. Okay? Yes?
Real quick, do you mind zooming in?
Yes. On the picture? Yes. Okay? Here's the next part. So let's say, we'll say we're specifically going to look at maybe a problem in which we are given that the velocity of A is 2 up and to the right meters per second. How can I use this equation to find out the velocity of B? Yep.
You know, SI and SB are changing at the same rate. Because they're-
Yep.
But inversely, BA is going up with 2 meters per second, speed is going down.
Beautiful, beautiful, excellent. So what this equation here from our derivative of the length of the rope tells us is that the time rate of change of SB is the same but opposite of the time rate of change of SA. So if SA is moving up and to the right at 2 meters per second, I can actually plug that in here and solve for the fact that SB must be 2 meters per second down and to the right. Now, what if somehow our length equation had given us this instead? What would that tell me? Yep, Samuel?
There is no pulley? No.
That they're both in the same direction.
They're moving in the same direction. 100%. The negative just says they're moving in opposite directions. If they're the same sign, it means they're moving this in the same direction. Now, in some of these later problems, when we add a nasty amount of pulleys, we might have something like this, which might tell us that one particle is moving with twice the speed as the other particle in the opposite direction. Okay? So let's do another example. I'm going to fix this so it matches the way I have it drawn. Let's do another example. So we've got a little bit more complicated system here. I have 3 different pulleys. Still 2 different particles, A and B. Let's look first at trying to maybe find those special points that define the length of this rope. There's actually a name for those special points. If we go up to my previous image, the book calls these datum, or reference positions, whatever you want to call them. But we need to choose where we're setting our datum. Any ideas for where I might set my datum? The central pulley, okay. I'm thinking in this first image, you should somewhat notice that I am trying to like isolate the parts of the rope that kind of change distance over time versus the ones that don't change distance over time. So if we zoom in on this middle pulley and I try to say, okay, I know that I don't care too much about the parts of this rope that don't change in distance, I can kind of somewhat ignore the part of the rope that lays over the top of the pulley, right? So this section between here and here, that never changes distance, right? So that's a good spot for a datum. And in fact, if I even extend this datum all the way to the left and I cross over this other rope, the piece above that datum also never changes position. So what I'm doing in blue here is I'm marking pieces that we're going to consider as like constant parts of the rope. So blue are the constant parts. Now tell me about pulley B. Is pulley B like fixed in place or can it move up and down? It for sure can move up and down, right? So again, let's zoom in on pulley B. There's a part of this where there's always going to be this much rope wrapped around the pulley. But then between here, there are certain distances, here and here. We probably need to give a name to that distance because that distance is going to change and it's going to be really important. However, tell me about how maybe the left side is related to the right side. Are they different or the same of each other?
They're equal.
They're equal. Yep. So whenever B moves down, the distance between the datum on the left is going to equal the distance between the datum on the right. So this might be, for instance, SA. And forecasting, when I write down the length of the rope, I'm going to have 2 SA, 2 quantities that are SA, plus some extra stuff. Okay, let's maybe zoom in on this final pulley. I'm going to, again, highlight the part that is not changing distance, right? There's always going to be that amount of rope wrapped around the pulley. And in fact, tell me about here. Does that distance ever change? Why not? Two fixed pulleys, yeah. So this pulley at the bottom is just anchored to the ground. It can't move up, it can't move down. Same for this one at the top. So this part in the middle is going to be a constant. And in fact, I can lump it in with the rest of my constant blue. All right, this leaves one section of the rope left. The last really important one. The distance between block A and this final pulley. That distance changes or doesn't change? It changes. So I'll label this, oh no, I did really bad. I labeled the distance that connects to pulley B as SA. I'm gonna change that and we'll say this is SB and we'll call this SA. Sorry, that was confusing. Okay, so again, this process of trying to figure out what parts of this system change in distance and don't change in distance is a learned skill that you'll have to learn by doing multiple of these problems. But hopefully you're seeing some commonalities about how I'm doing this. I'm looking for parts that are always constant versus those that are not. All right, so let's write an expression for the length of the rope. How might I write the length of the rope? Well, I've got some little constant here. I could call that C1. Plus an SB, right, this distance here. Plus another little constant here. Plus another SB. Plus another little constant over here. plus another constant down here, plus another little constant around this pulley, plus an SA. And in fact, I can lump all of those constant pieces together, yeah?
That was gonna be my question.
Yep. It doesn't really matter if I keep up with each of those constants because they're not going to change in time. And the expression that I really care about is the time rate of change of these variables. Because for the most part, I'm trying to relate the velocity and acceleration of one particle to the velocity and acceleration of the other particle, which are time rates of change. Okay, so all of these C's come together and I will have 1 SB, 2 SB, plus an SA, plus some constant. And if I take a time derivative, I get 0 equals 2 plus okay. Now, if I put one quantity on either side of the expression, we can start to talk about more about how they're related to each other. So maybe I do dSA dt equals minus 2 dSB dt. So tell me in words, what does this tell us about how the velocity of B is related to the velocity of A or vice versa? Let's say we're given the velocity of block A.
B would be twice the magnitude in the other direction.
Yes. Okay. If we are given the velocity of A, the velocity of B is double the magnitude but in the opposite direction. Now, opposite direction is a little bit strange for this problem. So sometimes it's worth thinking through visually in your head what happens when you pull one block in a single direction, right? So I can visually figure this out. In my head, if I pull on block A and I pull it to the right, does B go up or down? It goes up, okay? So when you're in kind of two different cardinal directions here because the pulleys change the direction by 90 degrees, that opposite direction is a little bit strange. So I try to do it by visual inspection. What if I move A, I call A moving positive, if I call that moving to the right, I can tell you what direction B moves, and then I know the opposite relationship as well. If A starts moving to the left, I get more rope on the left-hand side of the system, and B sinks downward. Samuel?
Isn't the velocity of B 1/2 the velocity of A? Because if you solve for B.
Yeah. You're right. Yes. Yes. Thank you. Yes. Oh, you had another question.
Same thing.
Okay, great. Good. Thank you for the correction. Okay. So we've talked about velocities. Is there any way that I can use a similar song and dance to relate accelerations? What would I need to do? Maybe look back up at those last two lines. Take another derivative. Yes, absolutely. That's always the answer when we want to go velocity to acceleration, right? What if we took another time derivative of this expression? What is the time rate of change of 0? Still 0. How do I take a time derivative of something that already has a time derivative? Take the second time derivative. Ooh, it's the exact same relationship for accelerations. If I am given the acceleration of A, then the acceleration of B is half the magnitude but in the opposite direction. Same relationship. Okay, that's all the theory for this section. Before I jump into examples, I'm going to go ahead and talk very briefly about our relative motion equation. All right, so relative motion, for the most part with relative motion, I'm not necessarily talking about two particles that are in any way connected to each other. They're just kind of hanging out in the same space. So let's say I have this Cartesian space defined by x and y. I might, for instance, have a particle A, and I might have a particle B. For this Cartesian coordinate system, how do I define the position of A? Can you tell me how to draw it? Yeah?
You draw a vector with its tail at the origin and its head at the end.
Beautiful. Yes. I'm just drawing the vector that goes from the origin to the particle. That is my vector r of A. So r of A is the absolute position of particle A relative to my fixed Cartesian coordinate system. So let's pretend A is U. A is U, and maybe the origin is your home. And you say, okay, I'm some distance away from my home, but I spot my best friend's house. And it's 200 yards in front of me and 200 yards to the right of me. I know the relative position between myself and my best friend's house. But what we might ultimately want to know is what is the relative position between my home and my best friend's house. And I'm going to give you an equation that will let us do that. So you're at A and you say, I spot B. I'm at A and I see that B is some amount forward and some amount to the right. We're going to call this vector the position of B with respect to A. The position of B with respect to A. We're going to find that there's a very simple relationship between the three vectors I've just drawn, where the blue one is the absolute position of B relative to the fixed Cartesian coordinate system. If you're good with vectors, You should know how these are related already. Anyone want to take a stab at how the three are related? Vector addition, brilliant. Specific. Is on the top of this more complicated term, this relative position or velocity or acceleration term. Okay, so here's another variation that is correct. I could actually say A equals B plus what goes on top and what goes on bottom of this slash sign. A goes on top, because that's the letter on the left. B goes on bottom. And the way that I read this, or the way that I read this term, is this is the position of A with respect to B. It's kind of like the way that we say derivatives. When we say with respect to, it's the bottom of that fraction. Like derivative with respect to time is the denominator of the dt expression. Okay, so I'm going to write my tip here. So if B is on the left, B is on the top of the fraction on the right. In fact, let me belabor this just a little bit so that you have it available to you in the notes that I upload. I'm just going to write that this is correct. And that this is incorrect. Okay. Question?
So is excuse me, is like the vector of v respect to a just the vector of a with respect to b, like equal magnitude opposite direction?
Absolutely. Yep. So that's what this line reads.
I thought that phrase sounded.
It's the same for all of them. Position, velocity, acceleration.
Thank you.
Yep. Okay. All right. That's all I'm going to say about relative motion analysis. Okay? So let's hop into an example. Let's go back to our dependent motion. And I'm probably going to need to make this bigger by a lot. Okay. We have a pulley system here. And I'm actually giving you a new component too. It's a special kind of pulley that has a motor attached to it. Okay? Sometimes we call this thing a winch or a hoist. Okay? So this thing up to the right is basically eating rope as it rotates. The rope is getting wrapped around a drum as it rotates. So rope is basically being pulled to the right at A. So it says determine the constant speed at which the cable A must be drawn in by the motor in order to hoist the load at B 15 feet in 5 seconds. All right. The very first thing I like to do with these problems is to try to analyze the rope and figure out where is a good place to put datum and to label different sections of distance. So let's maybe start with the right-hand side and follow the rope around the pulley system. The way that I like to think of this motor is actually to kind of get rid of it. I like to think of this as just the end of the rope being pulled to the right. Okay, so I could, for instance, give myself some datum here and say that as the rope gets pulled, that point is just going to move off into the distance towards the right, which means that the distance between the pulley and the end of the rope is one that is going to change. So I should probably label that with a variable. We'll call that distance SA. Okay. Then if we follow the rope around, I hit a section that's constant. It's just kind of wrapping around this pulley from here to here. That's never going to change distance. The next section is going to be between where we left off and maybe over here. Can this distance change? Some heads nodding. Saw one saying no. So you're kind of both correct. There is a part of this section that will change length, but there's a part that won't. So if I were to look between here and here, is this distance going to change in length? So I'm measuring relative from the center of the first pulley, wow, I'm short, to here, defined by the end of this kind of stick thing, this rod. Well, that rod can't change distance. It's a fixed, rigid body, right? So actually between here and here, that's also not going to change distance. So why don't we change where we put this datum? Let's say, all right, in fact, this part never goes anywhere either. But now this section can change. Okay, so this second pulley in the middle and this bottom two pulleys, they can come closer together or further apart as we pull in rope or we let out rope. So let's give that a name. We'll call that SB. Ooh, let's take the same logic when I turned this section blue. We can do that again somewhere else, can't we? The bottom part, yeah. So between here and here, those are also attached by a rigid body. So really, I don't care about that section either. This part, all the way through here, if I follow this rope, that never changes. This is the same distance as SB. This part of the rope never changes in distance. This part of the rope here, that's also SB. And guess what? So is this middle part. That's also SB. All right, how am I looking now? Do you think I've labeled every quantity that I need to label? All right, let's go for it then. Let's try and write our rope equation. I'm gonna zoom out a little bit. Let's say the length of the rope is equal to what? You tell me. Can you trace the rope around the same way we just did?
SA plus 4SB plus
Plus what?
C.
A constant. Beautiful. That is absolutely correct. Now I take a time derivative. I get 0 equals. What'd I do? Did I mess up?
No, he's making
No.
fun of me.
Oh, okay. Sorry. C goes to 0 because it does not change in time. Okay, so if we have dSA dt equals minus 4SB dt, what are we given in the problem? Are we given one of these quantities?
We're given DSB over DT.
Yeah, we're given exactly how much, at what rate we want SB to be moving. They gave it to us a little nastily. They said, instead of just giving us a velocity, they said you need to move 15 feet in 5 seconds. So let's interpret that. 15 feet in 5 seconds equals, I'm thinking 3, no, yeah? Yeah. 3 feet per second. And so if we know SB, how is it related to SA now? How do we interpret this? Yeah, we can just plug it in. Yes.
Did you forget the DSB or is that intentional?
Nope, I forgot it. Thank you so much. Yes. Sorry, I'm getting ahead of myself. I just get so excited about ropes. Okay. Now, once again, we have a pulley system where The opposite direction is a little bit weird. So if I pull A to the right, that means there's less rope available to the rest of the system. So does B go up or go down?
B goes up, but SB decreases.
B goes up because SB decreases. Okay, so that means in order to hoist load B up at 15 feet in 5 seconds, it means that we must wind the rope up at A by 12 feet per second. Questions here? Yes.
The 0 equals, so like that second line,
This one?
is it supposed to be negative order for any of those, or does it matter?
No. So as long as we followed through, so we started out with our rope equation, which means that I'm summing these distances, right? So these are all pluses on the right-hand side. When I take the derivative, they remain pluses. So the dSA dt plus 4 dSB dt, that's correct with the pluses. But when I take one of those quantities to the other side, it becomes negative. But to be honest, it's more of like the relative amplitude that matters about this expression. Personally, I like to think through the motion of the rope to figure out the directions. Because again, if A were pointed, let's say we were to take this motor, instead of having it out to the right, we took it straight down. Then this like opposite direction of one going up, the other going down, the opposite direction makes sense.
We can cancel it.
Well, it just makes sense that the opposite of one, like if one is up, then the opposite of that is down. It's not as clear to me here that for one to be to the right, the opposite of to the right is up. That doesn't make as much sense. But I can think through it logically by visually inspecting the system. I know that if I take A to the right, I can see how that's going to pull rope away from the rest of the system. It's going to shorten that distance between the other pulleys, right? And if that distance between the other pulleys is shortening, it must mean that B is going up. So I can visualize how going one direction causes the other to go in a different direction. Okay, all right. You will have more examples in homework of this, but we need to talk about relative motion. So let's do an example of our relative motion equations. And there is a nasty, ugly trick in this problem, I will tell you right now. But I kind of want you to stumble upon it yourself, okay? So I want you to go ahead and take a stab at this problem on your own. I have a funny feeling most people will fall into the nasty, ugly trick, and then we'll talk about it and we'll fix it together, okay? So let's do our normal think, pair, share. I'll give you, sorry, I can make that bigger. I'll give you maybe 5 minutes to get started, and then we'll go from there. VB is changing its speed. I think the speed is decreasing at -3 meters per second squared. And then the radius of curvature for B's path is 300 meters. Okay? And what are we being asked to find? Well, it says we need to find the acceleration vector, the acceleration of B with respect to A. That's what we're being asked for. Okay, so we're being asked for a relative acceleration, which should send off light bulbs in your head that we need our relative motion relationship, which is what we covered in class. And so let's fill out what that looks like. So the letter that's on top of the fraction on the right-hand side is the letter that also goes to the left side of the equal. And then the other one is on the right-hand side. So we know this relationship is true, which means that I can solve for my relative acceleration if I have acceleration of A on its own and acceleration of B on its own. Okay. So let's go on a hunt for acceleration of B, and then we'll go on a hunt for acceleration of A, and then we can plug them into this equation and solve for acceleration of B with respect to A. But actually, foreshadowing, it's going to be a little bit trickier than that, as you know from class. We're going to have to do a coordinate transformation, which is a little bit gross, but we're going to walk through it slowly. All right, so let's go on our hunt for acceleration of B. I know from my equation sheet that acceleration in terms of normal and tangential coordinates is v dot u hat t plus v squared over rho u hat n. And let's see, we can pretty much fill this out immediately from what we're given in the problem. So I'll go ahead and say the acceleration of B equals vb dot u hat t, but I'm going to be really careful with my notation here. When we talked about this in class, I'm being very careful to say that this is the tangential direction specifically for car B. And then I'm going to also be very careful over here to label this as the normal direction specifically for car B. And I say that because the tangential direction for B is not the same as the tangential direction for A. And nor are the normal directions the same either. And we can see that visually. If we go back up to our picture and we draw the tangential direction, well, if I look tangent to the path at A, we're right at the top of that circle, so my tangent direction should be perfectly to the left. Whereas for B, tangent to the circle looks like this. So this is u hat t A, and this is u hat t B, and they are not the same vector. They point in different directions. So we have to keep them separate. Okay? All right, so that's why I'm being really careful about my notation here. And now I can just fill in values. So VB dot is -3 u hat t B plus 31 squared over 300 u hat n B. Beautiful. I'm going to leave it at that for right now. Now let's do the same thing for acceleration of A. Okay, so acceleration of A then equals the time rate of change of the speed of A in the tangential direction for A plus v, the speed of A, the speed of A squared over rho A u hat n A. All right, and again, I can fill that out from what's known. I have a 25 u hat ta. Nope, sorry. Whoopsies. Ah. I have a 9 u hat t a plus 25 squared over 360 u hat n a. Brilliant. Okay, so let's move back a step. I said we wanted to find acceleration of A and acceleration of B so that we could plug it in to this equation up here and then solve for the acceleration of B relative to A. I want to solve for this by plugging in this and this. So let's do it. Let's do that. So I have acceleration of B. On the left-hand side, I have minus 3 u hat t b plus 31 squared over 300 u hat n b. And that's acceleration of A. That's acceleration of B. This is equal to, on the right-hand side, acceleration of A plus acceleration of B relative to A. Okay, that's all well and good. I could solve for acceleration of B relative to A and say acceleration of B relative to A equals everything here minus everything here. And the big bad pitfall that is looming, waiting to gobble you up, is that we cannot do this. I cannot say that this is minus 12 u hat t plus 31 squared over 300 minus 25 squared over 360 u hat n. I can't do that. I can't do that because these are not the same vector. So, for instance, it's not the same if I were to have 5 I hat and I wanted to add 10 I hat. I can do that because this is I hat and this is I hat. So I can add to get 15 I hat. But because this is not the same as this, I cannot combine those two things. Okay? So the big problem that I have to avoid, I have to figure out, is how to get these two accelerations into the same coordinate system, because currently they're in two different coordinate systems. One is expressed in a coordinate system for car B, and the other one is expressed in terms of a coordinate system for car A. So what we're going to do is we're going to do some trig. We're going to do some very kind of interesting trig, where I'm going to write the relationship between these normal and tangential coordinate systems and maybe an overall Cartesian coordinate system. So maybe I say, really I'm gonna choose a third coordinate system here, a common coordinate system that's terrible. X, Y, a Cartesian coordinate system that stays exactly where it's at. It's the exact same regardless of whether we're expressing the A NT coordinate system or the B NT coordinate system. We can relate both of those to the Cartesian coordinate system. All right, it's a little hard to explain, but I'm going to show you the mechanics of how it's done. So what I want to do, and what I do for almost any time when I have to be very careful about trigonometry, is I draw my two coordinate systems that I'm trying to kind of convert between. I draw them right on top of each other. And so let's start out with car A. Let's say I'm going to draw my Cartesian coordinate system that looks like this. X, Y. And then smack on top of that, I'm going to do the normal and tangential coordinate system that I that I already chose for A. Okay, so the tangential direction for A is directly to the left. This is my u hat t a vector. And the normal direction for A points into the center of the curve, or center of the circle, so it points directly down. Points like this, u hat n a. And now what I'm going to do is I'm going to write u hat t of A in terms of I hats and j hats. But just because of the position that A happens to be in at this time, it's actually going to be quite simple. And in fact, the tangential direction for A is exactly the same as the I hat direction. It points directly to the left, which is exactly where the x direction goes. The normal direction for A, it's not pointing up, which is the direction of the j hat direction, but it's pointing down, so it's perfectly opposite of j hat. So we say that it's minus j hat. Okay, so now what I'm able to do is I'm going to say the acceleration of A, if I go back up to my expression here, let me just copy and paste this. I'll make a copy of this. Copy. And paste. What I'm going to do is I'm going to substitute these unit vectors out for one another. So I can write this as 9, instead of u hat t comma a, I write I hat. Instead of u hat n comma a, I write minus j hat. And now I have an expression for the acceleration of A in terms of the I hat and j hat coordinates. And now I need to do the same thing for car B. Car B. So again, I'm going to put my coordinate systems smack on top of one another. I've got x, I've got y. But now the tangential direction for B points kind of up and to the left. I'll draw it like this, u hat t comma b. And the normal direction for B points into the center of the curve, which is down and to the left. So something like this. And the problem tells me that there's a 30-degree relationship right here. So this is kind of the tricky part. The tricky part is figuring out where this 30 degrees goes in this drawing down here. Where do we put the 30? Is it 30 here or is it 30 here? So here's how I try to do it. I say, okay, in this picture, there's 30 degrees between the vertical and the normal direction of B. 30 degrees between the vertical direction and the normal direction of B. If I go back down to my picture, I know there's 30 degrees between the vertical and the normal direction of B. Between the vertical and the normal direction of B, which means that this angle is 30 degrees and so is this angle. Which means that also every other wedge is also 30 degrees. So we could say this is 30 degrees. If we extend this back this way, then this is also 30 degrees. Now, why do I need to know that? Well, I need to know that because I want to write an expression for u hat t comma b in terms of i's and j's. And so I need to draw a right triangle that involves an I component, and a j component that together make up my u hat t b vector. So that's what I've just drawn in the black dashed line. So I have some amount that goes in the j direction, that's this one. This is going to be my j direction. And I have some amount that goes to the left, and that's going to be my I direction. Okay. So how do I write this expression? I can say that u hat t comma b is equal to 1 cosine 30 I hat plus 1 sine 30 j hat. Now, how did I know that? Well, I know that the u hat tb vector is a unit vector, so it has a magnitude of 1. Okay, so I have basically a triangle here where I have 1, I have 30 degrees, and I want to know how much are x and y. So I can say sine of 30 equals x over 1, opposite over hypotenuse. So the x component is equal to, did I mess up? Oh yeah, I labeled it wrong. I'm sorry. This makes more sense to call our y component, and this is our x component. Sorry about that. Okay, sine of 30 equals y over 1. And if I solve for y, I get 1 sine 30. So our y component is 1 sine 30. And I can say that cosine of 30 equals my x component over 1, because magnitude of a unit vector is 1. And I say my x component is 1 cosine 30. Okay, so that's my x component. Okay, that's still only part of the problem. I need to do the same type of expression for u hat n b. So let's draw the appropriate right triangle for NB. I'll have some amount that goes in the y direction. And note here that this vector is going downwards. So the y component is going to go in the negative j direction, not the positive j direction. But this vector also goes leftwards, which is the direction of positive x. So that will be a positive x component. Okay, so I can even draw this separately as well. I can say that this triangle is 30, this magnitude is 1, I have a y component and an x component. So sine of 30 is x over 1. So I have 1 sine 30 I hat. And cosine 30 is y over 1, but it's in the negative j hat direction. So minus 1 cosine 30 j hat. Okay, so now I have an expression for these two vectors in terms of i's and j's, and now I can do that substitution again. Let me go grab my expression for the acceleration of b, and we'll copy, and we'll paste, and I'm going to substitute. I'm going to say acceleration of b is equal to minus 3 u hat tb. So let's take our expression for u hat tb and plug it in. I have cosine 30 I hat plus sine 30 j hat, okay, plus 31 squared over 300 times u hat nb. Let's take our u hat nb expression and plug it in. I have sine 30 I hat minus cosine 30 j hat. And now we're done. Not entirely, but we're almost there. So now I have an expression for both the acceleration of A and the acceleration of B in terms of a common coordinate system. So now I can go back to trying to figure out this guy. So now let's take acceleration of B, which would be, I'm going to kind of rearrange things. So I'm going to try to get my I components together. I'm going to say that acceleration of B is minus 3 cosine 30 plus 31 squared over 300 sine 30 I hat plus minus 3 sine 30 minus 31 squared over 300 cosine 30 j hat. That's all on the left-hand side of this equal sign. Now we need acceleration of A, which is this one right here. So 9 I hat minus 25 squared over 360 j hat. Plus A, B slash A. And now we can solve for A, B slash A, and we can beautifully combine our I hat components all together and our J hat components all together. So let's do that. So if I bring this over to the left-hand side, I subtract 9 from my I components. I should have minus 3 cosine 30 plus 31 squared over 300 sine 30 minus 9 I hat. And again, this is all just a number. So you could take your calculator and reduce this down to a single decimal. That's totally fine. And then for j hat, I would have plus negative 3 sine 30 minus 31 squared over 300 cosine 30 plus 25 squared over 360. All of this goes with the j component, and that now is acceleration of B with respect to A. And that, my friends, is the end of the problem. Okay. Please feel free to rewatch, slow everything down, do as you will. Hopefully this helps, and I will see you all Thursday. Thanks, everybody.